We have discussed vertical asymptotes now in quite a bit of detail. Now we're going to look at the horizontal and oblique asymptotes on a rational function. First of all, we'll go back to our real basic rational function, and that is the reciprocal function. And this basic graph here that has both a vertical and horizontal asymptote. And remember, when we discussed this in our library of functions, we talked about the idea of the horizontal asymptote as being the behavior of the graph as the x values get very, very large in the positive direction or very, very large in the negative direction. I wouldn't say small because small usually implies close to zero. Okay, so I'd say large in the positive, large in the negative direction, or they approach infinity or negative infinity. Okay, and so when we study the graph of a rational function, the behavior of the graph as x approaches infinity or negative infinity is what we call our asymptote then, the horizontal or the oblique asymptote. And so for a horizontal asymptote or oblique, we're looking at the behavior of the graph as x approaches either positive infinity or negative infinity, okay? It's the behavior of the graph for large values of x in both the positive and negative direction. All right, so I would say, what does f of x do? I'm asking a question here when we're analyzing the asymptote. What does f of x do as x approaches positive infinity or as x approaches negative infinity? Okay, so really two different questions here, two different aspects. One is the positive side, one is the negative side, but in the end there's going to be a relationship there where they really should be the same result. Okay, typically with a rational function you won't have two different horizontal asymptotes or oblique asymptotes. You're going to have the same in both directions. Okay, so that's kind of interesting. So if I were to take a function like 1 over x and I start plugging in large values of x, and you can just kind of picture what happens here. You start plugging in very, very big values of x, like 1 over 100, then 1 over 1,000, then 1 over a million, 1 over 10 million. As you get further and further out in the x direction, the bigger the x is, the smaller that fraction gets, right? 1 over 100 versus 1 over 1,000. The bigger the denominator, the smaller the fraction gets, smaller and smaller. And that's why this graph will tend to get close to the x-axis, but never actually cross it, okay? Because as long as I'm plugging in positive numbers, 1 over a positive number is still positive, right? Positive over a positive. And so I can never hit 0, I can never get negative, but I'm continuously getting smaller and smaller, okay? Similar for the negative side, right? If I'm plugging in negative numbers, the answer is going to be negative, 1 over negative, right? Positive over negative is negative. So you're continually getting negative outputs, but those negative numbers are getting super close to the x-axis, okay? And that's the behavior of an asymptote. And so you want to think about what happens to the graph as you get really big numbers in there, okay? Well, generally speaking, 1 over x will approach 0 as x approaches positive or negative infinity, okay? And that's both sides, right? Now we have a little bit different notation for that. Often, instead of saying this, I would maybe put an absolute value on the x and say that it approaches infinity. The little bit simpler notation means the same thing. Either so the x on the inside could be positive or negative infinity, then its absolute value would always be the positive, right? So these two notations mean the same thing. So 1 over x gets close to 0. 0 then, y equals 0, is the horizontal asymptote. Okay? So whatever that value is going to be the horizontal asymptote. And generally speaking, whenever the denominator has a higher degree than the numerator, you're going to have the same thing occur. You're going to have 0 as the horizontal asymptote. Okay? Let me give you a reason as to why that occurs. Let's say I had a polynomial or a function, we'll call it g of x now to distinguish it. And let's do something like x squared plus 3x over x cubed minus, I don't know, 5x. Okay, something like this. Well, one way to argue or to explain what happens as x gets close to infinity or gets bigger, or negative infinity, is to change all of these terms to things that look like 1 over x. Because anything that looks like 1 over x or 1 over x squared, the denominator grows so quickly and the numerator stays the same that the whole fraction gets super small to 0. Okay? And so in general, as a general principle, 1 over x to any power really is going to go to 0 as x goes to positive or negative infinity, or the absolute value of x goes to infinity. Okay, so that's generally going to be the case, no matter what that power is. X squared, x cubed, as long as that power is a whole number. All right, so how do I turn each of these terms into a 1 over x or 1 over x to a power? Well, the answer to that is very tricky. You're going to multiply both the top and the bottom by 1 over the largest power of x. Okay, the largest power of x is x cubed here. So if I multiply the top by 1 over x cubed, and I multiply the bottom by 1 over x cubed, I'm multiplying the top and bottom of a fraction by the same thing. Well, remember, if you multiply top and bottom of a fraction by the same thing, you're multiplying by 1, right? This is essentially the number 1, just written in a weird way, right? Sometimes I write it this way. It kind of looks like I'm multiplying by 1, right? I don't know if you can even see that. My green marker's not working too well. Something like that. Does that look like a 1? Looks like a 1 to me. Anyway, so I'm multiplying by 1. It's not really going to change the fraction. It just changes what it looks like. Okay? And so when I do that, the end result is I distribute the 1 over x cubed to every term on top. Now, it makes a confusing looking fraction. Okay? A very complex fraction. Fractions inside of fractions. And what we get, this first term becomes x squared over x cubed, and the second term becomes 3x over x cubed. And then on the bottom, I get x cubed over x cubed. And then on the bottom here, I get minus 5x over x cubed. Well, if I go through and try to reduce each of these, I'm going to end up with the majority of these terms having an x on the bottom in the end, right? So I'm going to end up with, 1 over x for the first term. Second term is 3 over x squared. Here I get 1, right? X cubed over x cubed is just 1. And here I get minus 5 over x squared. Okay? And now it wouldn't matter what terms I had in here, if I had constant terms or filled in all the missing terms, as long as the bigger term is what I'm dividing by. Well, I know I can now figure out the behavior of this thing as x goes to infinity, because I know that anything with an x on the bottom and a constant on top is going to go to 0. So this essentially approaches 0 plus 0 over 1 minus 0, right? That's essentially what it's going to as x approaches infinity. Okay, that's essentially what it's becoming. Well, what's 0 over 1? It's just 0, right? So this graph is equal really to 0 over 1, which is just 0. So the function itself is approaching 0 as x goes to infinity, or the absolute value of x goes to infinity. And so what we're really looking at then is anytime the bottom degree is bigger than the top degree, you're going to find that the numerator all goes to 0, the denominator doesn't, and that creates a fraction. 0 over something non-zero is 0. So the horizontal asymptote will be right on the x-axis at y equals 0. Okay? So that's a general principle. And I did that with a specific example, but it generalizes no matter what the polynomial is on top and on the bottom. As long as the bottom has the bigger degree, then the same situation will occur where the 0, everything on top will become 0, everything on the bottom will become 0 except for one of the terms, and you get 0 over a non-zero, which is, of course, 0. Okay? So, as a general principle then, if the denominator has larger degree than the numerator, then the horizontal asymptote is y equals 0, or in other words, the x-axis. Okay? It will always be the x-axis, which is the equation y equals 0. Okay, whenever the denominator has the bigger degree. Okay, so now let's look at some other cases, because that's not always going to be the situation. You could have them as the same degree, or you could have the top as the bigger degree. Okay, so let's do a similar scenario here. This time, let's look at the case where the two have the same degree. Okay, so let's take an example like f of x. Maybe I'll move this down because I want a little bit of room to summarize on top. So let's take f of x equals, let's go x squared plus 4 over 3x squared minus 8x. Okay, we're going to go through the same process. I'm going to multiply the numerator and denominator by 1 over the biggest power. Okay, again, it's just a slick trick that will work to figure out what the horizontal asymptote is. And it will at least give us a rule. Okay, you wouldn't have to do this every time because it's going to become redundant. It's the same thing, but it gives us a rule that we can then follow. Okay. So what I'm going to do is I'm going to multiply this top and bottom by 1 over x squared and 1 over x squared. Again, remember, this is just the number 1 essentially, multiplying by 1. It doesn't change the fraction, it just changes what it looks like. All right, it's no different than if I took the number 2/3 and multiplied the top by 5 and the bottom by 5. Right, I'm multiplying by 1. It doesn't change the value. I would get, what, 10 over 15. The value is the same, it just looks different. Same thing here. The fraction is really the same, it just looks different. And so I'm going to distribute the 1 over x squared to both terms. And that will create, what, x squared over x squared plus 4 over x squared. And then on the bottom, I get 3x squared over x squared and minus 8x over x squared. Okay, so each of the terms just gets an x squared on the bottom, that's the biggest degree. And then I simplify each fraction. So this top fraction, that's a 1 plus 4 over x squared. Down here I get a 3 minus 8 over x. And again, the two fractions that still have x's on the bottom after it's simplified are going to go to 0. Right? So if I start plugging in really big numbers for x, positive or negative, these fractions are going to shrink down to 0. Okay? So this thing essentially approaches, I use the arrow to approach rather than an equal sign because it never really gets to infinity, right? You can never put x on infinity, you just get closer to it. And even closer is a weird idea. You never really get any closer because you're always an infinite distance away no matter how close you get. But you can get further from 0, I guess. It's kind of the same idea. So this thing will approach 1 plus 0 over 3 minus 0. Notice everything drops out, everything becomes a 0, except for these constants. Those stay the same, okay, as x approaches infinity. And of course, this occurs on both the positive and negative sides. And so this really just reduces down to 1/3, right? That equals 1/3. So that tells us the horizontal asymptote is at y equals 1/3. So it's a different value than it was with the 0. Okay. So the horizontal asymptote is y equals 1/3. Okay. If you look at the 1/3, that fraction is made up of the leading coefficients from the original polynomial, or from the original rational function, right? So the 1/3, those are your leading coefficients. And so as a general rule, and this will always happen, so again, imagine this, no matter what the terms are, no matter what the polynomials are, as a general rule, when you divide by the largest term, or the largest degree, you will end up with a ratio here where everything drops off except the leading terms, the leading coefficients will stay, and their ratio will end up being this horizontal asymptote. Okay, so that's going to always be the case. And so our general principle now is that if the two polynomials, the numerator and denominator, have same degree, then the horizontal asymptote will always be the ratio of the leading coefficients, whatever that is, okay? So if the denominator and numerator have the same degree, I need to erase a little bit here. Then the horizontal asymptote is the ratio of leading coefficients. Okay, it's going to be the ratio of the leading coefficients. Okay, pretty cool. No big deal there. Okay, now let's try it again. Repeat the process, but this time where the top has bigger degree than the bottom. This one's going to be a little bit interesting. All right, so let's take another function. Let's do something like f of x equals, now again, I need the top to be higher degree. So let's go x squared minus 5x plus 1 over maybe 2x plus 7. Okay. Now I'm going to repeat this process. I'm going to divide the top and bottom, or multiply by 1 over the largest power, which is x squared here. Okay. So I'm going to multiply by 1 over x squared, multiply by 1 over x squared. Okay. And then I'm going to distribute that 1 over x squared in. So this will become x squared over x squared minus 5x over x squared plus 1 over x squared. Okay, so basically each of those now gets a denominator of x squared, and the same can be said to the bottom. Right, so I'm going to have 2x over x squared plus 7 over x squared. Now again, we're just going to reduce each of those fractions. Okay, so x squared over x squared is just 1. Let's see, 5x over x squared is 5 over x. And 1 over x squared just stays as 1 over x squared. Then each of these, this will become 2 over x, and this one becomes 7 over x squared. That one actually doesn't simplify. Okay, so now I've reduced each of those fractions, and anything that still has an x on the bottom, but nothing on top, no x's on top, just a constant on top, will go to 0 as x goes to positive or negative infinity. And so this expression, or this fraction, will become 1 minus 0 plus 0 over 0 plus 0. Right? So everything that has an x on the bottom will approach 0, but this 1 doesn't have that x on the bottom. So now that occurs as absolute value x approaches infinity, or x approaches plus or minus infinity. And notice if I simplify this, I just get 1 over 0. Well, what is 1 over 0? What's anything over 0? It's undefined, right? This is undefined. Okay, well, because it's undefined, that means there's not going to be a horizontal asymptote, right? Because this is not actually a number, so y cannot equal something that's undefined. Okay, so that means there's no horizontal asymptote. Okay, and so that's actually going to be the case anytime that the numerator has larger degree than the denominator. Okay, you're not going to have a horizontal asymptote. You are, however, going to have something else, and that's the oblique asymptote, which I'll show you how to find in just a moment. First, let me summarize this. Although I'm going to keep that function because I'm going to come back and use it. Okay, so that was what? X squared minus 5x plus 1 over 2x plus 7. Okay, so we'll come back to that. So what I want to do then is give a little summary, and that's basically then, if the numerator has larger degree than the denominator, then there is no horizontal asymptote. Okay? Instead, there will be an oblique asymptote. Okay? And I will abbreviate oblique asymptote as OA, horizontal asymptote as HA. Okay? Okay, so now we've got to figure out how to find the oblique asymptote. Remember, I mentioned that an oblique asymptote is one that is on an angle. Okay? And so it's going to have an equation that represents a line. In fact, that equation is going to be in the form y equals mx plus b. So instead of just being a horizontal line, y equals a number, it's going to be a line on an angle. And it could be decreasing, it just depends on the problem. And it's going to be mx plus b as your equation for the asymptote. So let's take a look at how that works with this particular example. And so I'm going to erase everything else, but I'm going to keep that example since we now know that it doesn't have a horizontal asymptote. Okay, so now what we're going to do is we're going to take the function and we're going to divide the bottom into the top. This is why in a previous video we talked about long division and synthetic division. This is another application here. So we're going to end up either using long division or synthetic division to do this. Here I cannot use synthetic division because I don't have it in the form of x minus a number. And so I have 2x plus 7. The 2 kind of throws things off. So I'm just going to have to go with long division on this one. There are ways to tweak this so that I can make that happen, but I'm not going to go through that It's another longer process. So I'm just going to do long division with 2x plus 7 on the outside and x squared minus 5x plus 1 on the inside. So I've got my divisor and my dividend. Okay. Remember, the final answer is going to be the quotient plus the whatever we have as a remainder over the divisor. Okay. So if I divide this out, I always take the big term divided by the big term. So that's x squared over 2x. Well, that's x over 2, right? So x over 2, or equivalently 1/2 x, is my leading term, okay? Goes above the x term. Then I distribute 1/2 x times 2x is x squared, and 1/2 x times 7 is 7/2 x, okay? Then remember, our process for division is that you change the signs and draw the line, okay? So we're going to change, because we're subtracting here, so we're going to, that subtraction distributes, so it subtracts both terms, and draw the line, okay? And let's see, the x squares will drop off, minus 5 and minus 7/2. Well, we're dealing with some fractions, so I'll take that off to the side. The 5 is really 10/2, so it's a negative 10/2 minus 7/2, right? That combination. And that's going to end up being a negative 17/2, right, when I combine them. So that's negative 17 over 2x, and then I bring down the 1. Okay, now I have to do another division, and the division is big term divided by big term. Okay, so it's negative 17 over 2x divided by 2x. Okay, well, first of all, the x's will cancel. Okay, there's an x on top, x on the bottom. The 2's are a little bit weird. We got to be careful because they're both in denominators, and so here's what we're going to end up with. If I do this, it's negative 17/2, and remember, you copy dot flip. So I flip the bottom fraction, flip 2 over 1 to be 1 over 2, and I'm going to end up doubling that denominator. So I end up with a negative 17/4. Okay, so that's my constant, negative 17/4. And then I multiply that down. 17/4 times 2 is actually 17/2. It's negative 17/2 x, right? 17/4 times 2x is 17/2 x, and it has a negative. Then I multiply by the 7. Now this is going to get a little bit messy because it's 17. Oh, and it's a minus because I have a minus up there. And it's 17 times 7. 17 times 7 is 70 plus 49 is 119. So it's 119 over 4, okay? 119 over 4. Then we're going to, again, change the signs, draw the line, okay? So change the sign here, and draw my line, because we're subtracting those terms. And the x's will drop off. This 1 is really 4 over 4, right? To get a common denominator. 4 plus 119 is 123. Yeah, 123. So this is 123 over 4. Okay. Okay, so that's my remainder. Now this had some fractions in it. It didn't work out real nicely, but it still is doable, whether there's fractions or not. I assume my math lab problems are going to work out a bit better than this. Okay, so now let's get rid of some of this extra work on the side. So what does this tell us? Well, in the end, it tells us that the original fraction, which was the original function, I should say, which was x squared minus 5x plus 1 all over 2x plus 7, that original fraction is equivalent to the quotient 1/2 x minus 17/4 plus the remainder over the divisor. So that'd be 123 over 4 over 2x plus 7. Okay. Now if I think about that for just a moment, if I were to take the x value and run that off to infinity, make it approach infinity or negative infinity. These two terms, the constant term doesn't do anything. This term becomes infinitely large. Okay, so these two terms are still present. This one, however, with the variable on the bottom and the top being a constant, this will go to 0. So this entire term right here goes to 0 as x approaches infinity, or I should say absolute value of x goes to infinity. And so all you're really left with is this other stuff. This ends up being the oblique asymptote. Notice it's in slope-intercept form. Okay, so we have our oblique asymptote. It's everything that occurs off of the, that doesn't include this remainder term, because this remainder term is what goes to 0. Okay, what you end up with is a graph. Now 17/4 is the same as 4 1/4, right? So this could be seen as 0.5x minus 4.25, right? 4 1/4. So you're going to have a graph. I probably should have made that dashed because it's an asymptote. Okay, close enough. There's my dashed asymptote. It has a y-intercept here at negative 4.25 or negative 17/4. It has a slope of 0.5, so for every 1 up it goes over 2. 1 up over 2, right at 1/2. And now if I wanted to really get a good sketch of the graph of this thing, I would need my vertical asymptote as well. My vertical asymptote occurs when my denominator is 0, which is negative 7/2, right? If I set that equal to 0, subtract the 7, divide by 2, it's negative 7/2. So, which is negative 3.5. So that's my vertical asymptote. Something like that. Now I'm not putting a scale in, I'm not being real careful with this, just give you a general idea of what it looks like. And then the question is, how do I determine where this graph is, right? Where does it, is it up here on the top right? Is it on the bottom left or bottom right? Top left, bottom left, where is it going to be? Well, it cannot be in both the top right and bottom right because it wouldn't pass the vertical line test if it was. So you're either going to have top right with one of these two or bottom right with one of these two. You can't have, you can't have both the top and the bottom on the right or the top and bottom on the left. So how do I figure it out? Well, you would plug in some numbers mainly, and we'll get into this in the next couple examples when we actually plot the details of these graphs. But you would plug in a couple numbers, like you could plug in, plug in 0 into the function and see where the function is. If it's above negative 4.25, then the graph is up here. If it's below, then it'd be down on the bottom. So just real quickly, if I plug in a 0 to the original function, I'd get 0 minus 0 plus 1, that's a 1. 0 plus 7, that's a 7. 1 over 7 is 1/7. So my graph, my y-intercept is up here somewhere at 1/7. So that pretty much tells me that my plot's going to be up above and to the right. Okay, oops, I kind of drew that. I drew that poorly. It almost doesn't pass the vertical line test the way that I drew that. There. So we approach the vertical asymptote, we approach the oblique asymptote. What you end up with is this function approaches this line as you get closer to infinity or further out from 0, and the difference between the graph and that line is really built into this remainder term. Okay, this remainder gives you the distance essentially between those two graphs, the line and the actual graph itself. Okay, so then the other side, it's either going to be up here on the left or down here on the left. To figure that out, again, you could plug in a number and see whether it's above or below that line. Maybe I would plug in, it's got to be less than negative 3.5. So if I plug in something like negative 4, I should be able to make that determination. Let's get rid of this. So f of negative 4 is going to be 16 plus 20 plus 1. I'm going to do this quickly, plugging in negative 4. This would be negative 8 plus 7. If I calculate that, that's going to be 21 and 16 is 37 over negative 1 is negative 37. I think it's safe to say with a negative 37 as my output that we're down below the down below this line. If I wanted to make sure, I would plug that negative 4 into the line itself and make sure it's higher than negative 37, which it will be. Negative 4 in here times a half is negative 2. Negative 2 minus 4.25 is negative 6.25. So there's no doubt this is further down than the line itself. So our graph is going to be down here and probably approaching this. It'll look something like that. I didn't draw the asymptotes out, but if you extended it, that's something like what it would look like. Okay. Okay. And plus, you can also guarantee that also without even having to plug in that second value, because I know that the vertical asymptote comes from a 0 of multiplicity 1. It's an odd multiplicity on the bottom, right? It's 2x plus 7 raised to the 1 power. And so because it's an odd multiplicity, I know one side goes to positive infinity, the other side must go to negative infinity at that vertical asymptote. And so that's another way to just check it and make sure, even without having to plug that in, I just know that that's going to be the case, so I could assume it's going to be down here below. Okay. Okay, so that gives you an idea, kind of an overview of your 3 different situations. Again, if the numerator has higher degree than the bottom, than the numerator or the denominator, then you're going to have an oblique asymptote, and you find it by dividing, either by long division or synthetic, whichever one works best for the situation. If your degrees are the same on top and bottom, you'll have a horizontal asymptote at whatever the ratio of leading coefficients is. And then if your denominator has the larger degree than the numerator, then your horizontal asymptote is on the x-axis at y equals 0. Okay, so those are your 3 scenarios.